Hey there, this is Arnav from Pebble, and welcome back to the Introduction to Linear Algebra. In this video, we're going to start talking about vectors and vector spaces and what we think of them in the linear algebra world. And before we get into that particularly, I just need to talk about a quick little piece of notation, which is R, should be an R of n. And you'll see this R with these two lines. I'm not very good at drawing it, but it looks something like this. That's just really bad. My apologies. So R of n, and what I'll do is I'll copy this. So you can see how bad mine is compared to that. But anyway, what R of n is basically saying is that this is just a set of all n tuples. So a tuple could be something like an ordered pair, like 1, 2. This could be a tuple. And it's really just this is a 2 tuple and it has dimension 2 because it's a 2 tuple. And so this belongs to whatever Rn is because this is a set of all n tuples. So something like 1, 2, 3, 4, this would be a 4 tuple. This also belongs to Rn because Rn is the set of all n tuples, which means it can go just to n, which is just unbounded. So what this is we're gonna call it an n space. Okay, so the set of all n tuples is going to be referred to as the n space. And so something that we could do here is this particular tuple, it's of dimension 2, so what we could also say is that it belongs to the 2 space, which would be the set of all tuples with dimension 2, of all 2 tuples. And then this would belong to the set of all 4 tuples, or the 4 space, because it's a 4 tuple and has dimension 4. And so what this is going to be basically the main basis for what a vector space is, because vectors are essentially column matrices that are just one row, right? So when you have encountered vectors in previous math, you might have seen something like 1, 2, 3, 4 being a 4-dimensional vector. And if you were just in physics, something like 1 and 2 would be a 2-dimensional vector, right? And while we represented it with row matrices, while we were talking about our n space, this could be very similarly something for a 2 space. And that brings us to our definition of a vector space. So a vector space, we're basically just going to say, is a set of all objects. It is a set of all objects that have these certain properties. Okay, in an n space, we had that the property that they had to meet was that they had the same dimension. And in a vector space, it's going to be that, but they also need to have, but we're not bounded by dimension in this case. So it's just going to be a set of all objects that have a certain set of characteristics. Okay? And all the objects in this set are going to be vectors. So a vector space of all objects with certain properties. And then a vector is going to be all objects inside a vector space. It's going to be an object, not all. An object inside a vector space. And so N-tuples, like we just discussed, are a type of vector space with row matrices. Okay? But we now need to formally define what characteristics that they have to meet. Okay? So we're going to define these. There are 10 characteristics that they have to meet. Okay? So 10 properties for a vector space qualification. First one is going to be, and these are separated by two categories, addition and then by scalar multiplication, which are the two operations you can do with the vectors, if you remember from previous encounters. So addition and scalar multiplication. So A1, we're just gonna put the letter and then the number, just to denote these easier. Closure under addition. So what this is saying, that if we have a vector u and we were to add it to v using vector addition, this is just a symbol for vector addition, then this also needs to belong to our vector space. Okay, so if u and v are both in the vector space, then u vector added to v needs to belong in the vector space in order for it to be a valid vector space. And so A2 is commutative. So if u and v belong to a vector space and you do u plus v, this needs to equal v plus u. So when you add the two vectors, regardless of the order, the sum still needs to belong to the vector space. And then A3. So this is associative. So if you have three vectors u, v, w that belong to our vector space, then you can associate them in any way. So this just ensures the associativity of vectors inside your vector space. So you could do something like this. And this would have to be equal. Okay. A4 is going to be that v needs to have a zero vector, which is going to be denoted by 0. And that basically is going to say that for every vector u that's in v, u plus 0 is going to equal u, obviously. So there needs to exist a 0 vector. Okay, and then A5 is going to be that for every vector in u, you need to have an additive inverse of u, which just means that if you have u, you also need to have some vector minus u, that when you add it to u, it's gonna equal 0. So if this condition is true, then that means that it'll work out with your workout. So I'm gonna move this down here so I have more space. And we're gonna say that S1 So the first one in scalar, this first condition, is that scalar multiplication has to have closure. Okay, so if u belongs to a vector space, then if you have a scalar alpha and you multiply it with u, then this needs to belong to your vector space. Okay. S2, if you have two scalars, a and b, alpha and beta, and a vector u, in the vector space, then alpha times beta times u needs to equal alpha beta into u. Okay, so that's pretty, again, similar to associativity. That just, you need the associativity in vector spaces. And then S3 is going to say that for any vector inside our vector space, one cross product with u is going to equal u. Has to. Always. For any vector. Okay. And then if you have S4, if you have two scalars alpha and beta, and then you also have your vector u that belongs to the vector space, then this is basically just distributivity of scalar multiplication. So alpha plus beta into u has to just equal alpha dot u plus beta dot u. Make sense? And then S5 is basically saying that if you have a scalar alpha and then you have two vectors u and v that are both in your vector space, then this is again distributing in a reverse manner. So S5 is basically just saying if you have alpha dot u plus v, and then that has to equal alpha dot u plus alpha dot v, basically. And so these are the 10 conditions that you need to have for a vector space. And so even if one of these does not work, then you don't have a valid vector space. Only if all 10 work, then this would be a valid vector space. Okay, and remember the vector space is just a set of all objects that have these properties. Okay, so you could have multiple different sets of objects, but whatever they do, whatever all your vectors in that vector space are, they have to meet these qualifications. Otherwise, it would not be a valid vector space, and it would just be a set that it's not that great of a set, right? And so one thing to note is that if your scalars, if all these scalars if you restrict them to be real numbers, then your vector space is going to be called a real vector space. And if you allow them to be complex numbers, then you can call your vector space a complex vector space. Okay, and normally, just for the sake of this course, we're just going to be going over real vector spaces. And so rarely you'll see a complex scalar, but if we do, then we'll definitely mention it. And we'll definitely go over it in a bit more detail. And obviously vector spaces are sets, so we should be using set notation for this. So if we're to say that we have, let's take an example. We have this vector xyz. We have this vector xyz, and we want to denote a set. for everything where x is always 0. So we're gonna say that we're gonna use set notation here. X, Y, Z is gonna belong to, since vector spaces are set, we can use belong to, and this is gonna be the set of all real 3 tuples, because this is the 3 space, remember? And then where x is equal to 0. So this bar here means such that. Okay, so this would be your valid set notation for your vector. And yeah, so if you were to want to determine whether this is a vector space, then the approach here would be to go through each different condition and then prove that every single one is a vector space. Okay. And so I'm thinking that we need to, I think we need to go over a couple theorems that are pretty self-explanatory, but it would do you good to just take a look at them in detail a bit. So the first one is that for any vector in a vector space, let's say u again, 0 dot u is just going to equal 0, the 0 vector this time. Okay, and the difference here is that this is your scalar 0 and this is your vector 0. So normally this would be denoted in a bit of bold, but I can't do that obviously with my pen. Okay, and then theorem 2 is just going to say that if you have a scalar times the 0 vector, maybe I'll denote the vector like this. Okay, so times the 0 vector, and then that's just going to equal the 0 vector. Okay, and then the third theorem that you're going to have is that additive inverses are unique, and this is pretty simple to prove because, let's just say you have 2 additive inverses, let's just think you have 2 unique ones. Well, you can see that these two clearly have to be the same thing, obviously. So it just logically follows that they are unique. And then the 0 vector in a vector space is always going to be unique. So this has to be unique no matter what. And that's pretty simple. And then for a vector, for any vector, you in your vector space, -1 dot product with u is just going to equal the negative of the vector. So this follows two rules, sort of. The one where you have to make sure that there's always negative, and then you have to make sure that you can always multiply by scalars. So the scalar multiplication exists, and then also the negative exists. So that makes that makes sense. And then one other thing is that the negative of a vector, the negative of a negative in a vector in a vector space is just going to equal the original vector. So this logically follows from everything you've learned. And then another thing is if you have a scalar times a vector and that equals 0, then either the scalar has to be equal 0 or the vector has to equal 0, obviously. And yeah, that pretty much just sums up the theorems that you need to know for vector multiplication. And yeah, that's vector spaces for you. And in the next video, we'll hopefully be getting into a bit more of subspaces and in future ones, we'll start getting into the meat and potatoes of vector spaces. And I'll see you there.